Video, let's see if we can understand knowledge distillation, the technique that was used to create DistilBERT, which is a more efficient and compact version of the large and powerful BERT LLM. Here is the core idea behind knowledge distillation. See, the student has to, it's given a hard target. It has to get the right answer. There is no doubt about it. But in addition, the student model, the student neural net also has to learn other things that the teachers or the teacher neural net considered but did not finally choose. Okay. Maybe this will become even this core idea will become clearer if we look at this one example. This one was given in the paper itself, right? Those who created DistilBERT. So this is called soft targets. The hard target is the right answer, and the idea of soft targets in classification. Look at a classification task. Look at this toy example that I just created. We know that finally the model is going to choose one class. It so happens in this case it's the green bar. Let's say it has a probability of 0.8 or more, and the class 2 is what it will pick. But look at class 1 and class 3. They have very, very tiny probabilities, but they are non-zero, right? As the paper itself says, some of these quote unquote almost zero probabilities are larger than the others. And this is the key idea, this reflects the generalization capabilities of the model. Okay, so the student model has to learn not only the right answer, but also all these near misses or almost zero things that the teacher considered. And that's how it learns to generalize about the whole world. And I really like this example that they gave. If a student or if a model is trying to predict something about a desk chair, it sort of understands that armchair is a related concept, but no good model should get confused between a desk chair and a mushroom. Okay, so an armchair in this case is also a soft target. So I have one example for this idea behind how this generalization works. So hopefully that will make things clearer. I took a very simple example. Let's say that an LLM had to come up with the capital of France. Okay, the hard target is very easy, and we know, of course, it has to finally arrive at Paris. But while getting there, perhaps it also considered things like, right, other options or candidates. It may have considered things like London, Madrid, and Rome, right? We know why, because these are other European capitals. But a model may also have considered these three options. Again, why? Because Marseille, Lyon, Toulouse happen to be other large cities in France. It may even have considered things like a baguette or croissant with lower probabilities, perhaps, because they co-occurred whenever France and Paris showed up, maybe baguette and croissant showed up. Okay, so all of these are the soft targets of the teacher, and these are the ones that a student has to learn. Okay, so again, to emphasize, the student LLM is trained using the teacher's soft targets. Okay, all those candidates in addition to Paris are the soft targets for the teacher. And if any of you are even slightly mathematically or statistically inclined, I would highly encourage you to read up on cross entropy loss or KL divergence. In fact, in the description of this video, I will try and I will link to other videos. People have created wonderful videos explaining these. And the idea is very simple, right? From a teacher's probability for PMF, right? And a student's PMF, how do you compare two probability mass functions? And this cross entropy loss happens to be one way of doing it. So over a period of time during its training, the student tries to learn how the teacher quote unquote thinks these two probability functions or all these targets match each other. As this cross entropy loss goes down, the student is learning. And this is the core idea behind knowledge distillation. This is back to where I started with, right? I started with DistilBERT, which is a compact, concise version of BERT. And what does all this mean? Okay, it turns out that BERT, which has 12 transformer layers, okay, whereas the people who started creating DistilBERT, they chose an architecture with only 6 transformer layers. Right away, that's a 50% reduction. Okay, and on top of that, while BERT has 110 million parameters, DistilBERT only has 66 million. It's not quite half, but 60%. Okay. a very good gain. So DistilBERT is only 60% or 50% of the size of the parent BERT model. But what does all this mean? As you know, every LLM has so many different benchmarks. And without getting into the details, so from the paper, from the DistilBERT paper, they say that when they looked at it at a macro level, they call it a macro benchmark, an aggregated benchmark. While BERT was able to score 78% on a particular benchmark, on that exact same benchmark, the skinny down, smaller DistilBERT scored 75.2. This is quite impressive to me, right? That you lost half your layers, 60% of the total parameters, and yet you only dropped by not even 3 percentage points. So to me, this is very impressive. Later on, I was thinking about it, and I don't even know if this is the right way to go about it. But let's say that you wanted to go in the opposite direction. Okay. So let's say that you started with a model of the size of DistilBERT and wanted to improve its performance. So in order to gain, right, not even 3 percentage points in benchmark, you would have to double your transformer layers and nearly double the number of parameters. At least to me, this gives me an intuition for why LLMs are growing larger and larger. It was a quick look at how knowledge distillation works using DistilBERT, a smaller version of the larger BERT model, as a real world example. Thank you for joining me. I hope that was somewhat useful.